Hi everyone, welcome back to the channel. My PhD is coming to an end, my thesis is submitted and my defense date is finalized. So I created this small video to cover the background that is needed to make the most out of my thesis defense. Okay, so let's get started. So let's start with Boolean decision rules. Okay, so let's say we have this kind of a data set where our X are our features, right? So all of them are binary features, right? So they only take 0 and 1s, right? And we also have this something called binary target values, which are also 0s and 1s. And we want to predict this target values using something called a Boolean decision rule. So what a Boolean decision rule looks like is something like this. So this is how a Boolean decision rule looks like. Okay, so it is basically a bunch of ors of ands, right? So everything that is in the parenthesis, right? So they are called clauses. And so for this Boolean decision rule to be evaluated to true, one of these three clauses must be satisfied. Okay, so let's go through the example and see whether how this is working on this particular example, right? So let's look at this first row. So it says that either x1 and x3 has to be true, or x2 and x4 has to be true, or x1 and x5 has to be true. If any of these three clauses are satisfied, then we will predict our target to be 1, otherwise it will be 0, right? So for the first example, x1 and x3 is definitely not satisfied, but x2 and x4 is satisfied, right? So this one is satisfied and therefore we predict it as 1. For the second example, we have x1 and x3 is satisfied, right? So here again it is 1. So only one of them needs to be satisfied, right? So the other two we don't really need to care about. So for the third one, none of these three clauses are satisfied, right? So you can check if you want by pausing this video. And none of these three clauses are satisfied. So therefore this here we predict the target value as 0. Okay, so this is actually the given training data, and our Boolean decision rule is actually predicting the target, right? So it may not actually always match with the given target values. So for the fourth one also it is kind of matching because x2 and x4 is 1. So this clause is satisfied, therefore it is 1. But for the fifth one, the actual target value is 0. But here we can see that x1 and x3 is 1, right? So x1 is 1, x3 is 1. So this particular clause is satisfied. And therefore this Boolean decision rule evaluates it to be true. And therefore the target should be 1, but it is actually 0. So in a way, for this particular training data, this Boolean decision rule is not the best one, right? So what we want to do is we want to generate something like this, some sort of formula like this, and which is slightly more accurate, right? So than this. So one of the key advantage of having this kind of a Boolean decision rule is that it is very, very explainable. So in a sense that if you look at the first example, right? So it was classified as positive. And so we can point it out why it was classified as positive. So because it was classified as positive because x2 and x4 were set to 1. This is some sort of an explanation for why we are classifying something as positive or negative. So negative is very simple, that none of these things are satisfied, therefore it is classified as 0. But for the positive, it is giving like very, very specific pinpoints, right, why it is classified as positive. This is something that other classifier does not have, right? So for example, if you talk about neural networks, right, so it can very accurately predict all of these targets if you have even large data and lot more features and everything, but it cannot really give you this kind of an explanation. So that's something that is very, very desirable about this Boolean decision rules. Okay, so our goal is to generate this kind of Boolean decision rule for this data set, hopefully something that is better than this one. So how are we going to do this is basically we are going to assign some variables for each and every clauses, right? So let's say I listed down all the clauses of size 2, and I've assigned some variables, which is w1, w2, w3, w4, and so on and so forth. So our goal is that we want to select some of these clauses to be in our formula, final formula, right? So one clause or the other clause or the other clause and so on and so forth. That's what our formula looks like. So we want to select some of these clauses to be in our formula. So if you look at the first example, right? So it has x2 and x4 are 1 and nothing else is set to 1, right? So x2 and x4 is, where is x2 and x4? x2 and x4 is over here, w6. So if we want to make sure that the first example is classified as positive by our Boolean decision rule as well, then our formula must include this x2 and x4 as a clause, right? So we are going to say that for our input 1, w6 has to be greater or equal to 1. So that's one constraint, right? So if you look at the other two positive examples, right? So for example, this one. So here we have multiple choices. Either x1 and x2 can be 1, or x1 and x3 can be 1, or x2 and x3 can be 1. Any three of these clauses can be 1, and as long as that happens, then we are going to satisfy this, and we are going to classify this example as positive, right? So if we look at it in form of the constraint, then we can write it as w1 plus w2 plus w5 is greater or equal to 1. So what is w1, which is x1 and x2, w2 is x1 and x3, and w5 is x2 and x3, right? So any one of these three clauses is, if it is there in our Boolean decision rule, then kind of we are safe in terms of this second input, right? So we'll talk about the third input in a minute, but let's talk about the fourth input. It's kind of similar to the second one, right? So again, like we have three possible clauses that can help us classify that example as positive, right? So if we just write it down, it will look something like w6 plus 7 plus 10 is greater or equal to 1. Right? So if you want, you can just pause the video and see that this is, I did basically the same thing that I did for input 2. Okay. So now let's talk about the 0 example, right? So we want to avoid clauses that are satisfied by these 0 examples, right? So if we include those clauses in our formula, then these examples will be classified as positive, which we don't want, right? So for this one, we have x3 and x4 should not be there, right? So x3 and x4 is w8. So we want to avoid w8. Right? So we want to avoid this particular clause to be in our formula. Similarly, for this example, we want to avoid three different clauses, right? So which is x1 and x3, x1 and x5, and x3 and x5. All of three we want to avoid, right? So if we write it down, so that essentially we want to avoid this w8, w2, w4, and w9, right? So this essentially captures the requirement for generating our Boolean decision rule. And if we just try to solve it manually without any like formal software or anything, then it is still like, it's a very small example. We can actually solve it, right? So clearly w6 has to be equal to 1, right? So as because like, you know, there is no other way to satisfy this constraint, right? So w6 is 1. So as soon as we pick w6 in our formula, then in fact our input number 4 is also covered. Okay. So w6 is 1, so we can actually even add more things, but let's keep our formula short, right? So let's say w6 is there, so 1 and 4 is kind of covered. And for the input number 2, we have three choices, but we want to avoid this w2, right? So we don't want to select this w2. So we are left with w1 and w5. Okay. So for me, it is kind of, both of them are kind of similar. So I'm going to pick w5. You can actually pick even w1 as well. And so once we do that, we are actually covered with input number 2 as well. So our formula would look something like this, which covers all three of these positive examples, and it actually avoids clauses which are present in the negative examples, right? So this formula for this data set gives 100% accuracy. Okay, so this is a small example, so we could do it, but like for a bigger example, it might not be possible to, you know, satisfy all of these constraints, and it might not be possible to avoid all of this constraint, right? So what we can do is we can actually add something called a positive penalty, the penalty for the positive variables, which will look something like this, right? So for the input 1, I'm adding one more variable xi1, right? So if I cannot select w6 for some reason, right? So in that case, what I want to do is I want to set up this penalty variable xi1, and I want to minimize this penalty variable xi1. Same for the input 2 and input 4. I want to minimize this xi1, xi2, and xi4, right? So they should ideally be set to 0, but in case if we fail to pick any of these clauses, then we'll have to set them as 1. So they are basically misclassified. Similarly, we want to avoid this variables like, so 8, 2, 4, and 9. So we are also going to put them in our objective, and we want to minimize these variables as well, right? So we want to ideally set them to 0, but in case if we can't, then we'll call that as a penalty for the negative examples. So notice that all of these things is linear, right? So constraints are linear, objective is linear, and all of this entire model is actually created by Sanjeev Das and others. So they actually did a lot more than just this. So this is like a very basic, overview of what they did, like how to generate Boolean decision rules. But this is not the entire work, right? So let's talk about where column generation comes into the picture. So that's where their actual contribution lies. So we talked about the size 2 clauses, but what about the bigger size clauses of like say size 3 or size 4 or size 5 clauses, right? So all of these have only 2 variables in the clause. It can have more than 2 features. So let's talk a little bit about that. Okay. So there are some advantages of having this kind of bigger size clauses, and there are some disadvantages. So let's talk about the advantages first. Okay. So they actually help with better accuracy. So if we have a bigger size clauses, if we allow this kind of bigger size clauses, then we can generate clauses which are only satisfied by the positive examples and not really satisfied by the negative examples. This can actually help us get like better accuracy. The disadvantage of this kind of clauses, one of the disadvantages is that it makes this formula harder to read. If we have very, very large clauses, then the key advantage of this formula being interpretable and explainable, it is kind of gone, right? So I don't want to say that this example is classified as positive because this list of 100 features are set to true, right? So that's kind of a meaningless explanation. So to cover that, they introduce one more linear constraint like this. So what is this? So this is actually, they introduce this kind of complexity notion for every clauses, right? So we have this W variables, and for every W variables, there is something called a complexity of this clause. So what is the complexity of this clause? It is basically the size of the clause plus 1. Right? So every time I add one more clause, I'm already adding 1 to the complexity plus whatever is the size of the clause. So if it is like say size 3 clause, then the overall complexity introduced by selecting that clause is 4. Right? Similarly for bigger size clauses, basically this says that we want to avoid bigger size clauses as much as possible. We want to favor more smaller size clauses. And this entire complexity, right? So set of all possible clauses that we select, and if we multiply by their complexities, then all of that sum should be less than equal to some capital C. That's an hyperparameter, right? So we can say that, my overall complexity of the Boolean decision rule should be less than equal to say 10 or 15. I mean, basically it depends on how much do you want to care about getting better accuracy, or do you want to care more about formula being easier to read, right? So that depends on what kind of C do you choose. Okay, so this issue is kind of more or less taken care of. But there is one more issue, which is there are too many of them. So if we let's say if we have 100 features, right? So how many possible clauses are there, right? So including all the size 2, size 3, size 4 and all size of clauses, then we'll have 2 raised to 100 possible clauses. So that's just too many of them, right? So our linear program will have just way too many W variables, and that's not something the computers can handle. So how do we solve this? It's basically we solve this using column generation, right? So we generate this W variable only when they are actually needed. So at this point of time, if you are familiar with column generation, how it works and everything, then you can actually skip to the decision tree by clicking on the timestamp that is mentioned in the description. But if you are not familiar with what column generation is, so then just stick around, right? So I'm going to briefly explain the idea behind column generation now. Okay, so the idea is that there are just too many of them, and we want to tackle that issue. So let's consider again our linear program, which was something like this. So what I'm going to do is I'm going to actually solve this linear program using simplex, and I'm going to demonstrate that most of these W variables are going to take 0 values, and only some of them are actually needed for this solving process, right? So that's the key idea, that they can be actually omitted from the linear program from the beginning, and they can be only added when they are needed, right? So let's see how the solution process works. So the first thing that I'm going to do is I'm going to subtract something from this left hand side to make all of this inequalities as equalities. That's a standard process for solving these linear programs. So once we do that, I'm also going to do some more thing, like I'm going to rearrange these variables in this manner, right? So I'm going to keep all the xi variables on the left hand side and everything else is on the right hand side. So why I want to do this, I'll just explain in a minute. But the idea is that I want everything on the right hand side to be 0 and only left hand side should be non-zero, right? So all of these things are 0 and all of these things are non-zero, and that's how we get to our feasible solution. So we also need to take care of the objective part, right? So we have this kind of expressions for xi1, xi2 and xi4 in terms of equalities. So that's why we wanted to actually have these equalities instead of inequalities, right? So we can actually substitute xi1, xi2 and xi4 in the objective by these expressions. And if we do that, it will look something like this, right? So all of these things are in our desired format, right? The xi variables are on the left hand side. Everything on the right hand side is 0 xi variables are 1, 1 and 1. So which is in other way, it's like I didn't select any of my clauses. So therefore all my penalty variables are set to 1. My objective has only variables that are taking value zeros for now. And therefore the objective value for this particular solution is 3. Right? So we already have a feasible solution without really doing a lot of work. And now our goal is to find a solution that has a better objective than 3. Right? So that's what we'll try to do. So notice that in our solution, W5 is taking the value 0, but it has a negative coefficient in the objective, right? So these coefficients, they are called reduced cost, right? So that's an important term, just you need to remember that. So essentially it is like the formula that you get, the coefficient that you get after, this kind of rearrangement of variables, like substitution and everything. Right, so it has a negative reduced cost. What does it mean is that if we try to increase W5, it will hopefully decrease the objective value. Right, so that's what we want to do. We want to increase W5, but we are also going to stick to our standardization where everything on the right hand side we want to keep it as 0. So we'll move our W5 to the left hand side. So there are two places where W5 appears, this one and this one. So I'm going to use this one, but you can use other one as well. Essentially, you want to use the one which will restrict the W5 the most, and in this case, both of them restrict the W5 to take maximum value, which is 1. So we are kind of fine with either of them, right? So I'm going to pick this one, and let's say if we move W5 to this side, then it will take value 1, and xi2 over this side, so it will take value 0. So when we do that, it will look something like this. So once we have an expression for W5, we are going to substitute that in all of the other equations, including the objective, and it will look something like this. And the first constraint is simply just not affected, right? So notice that we are immediately at a better objective, which is 1, because that's how the rearrangement worked out, and it had a coefficient 2, so it actually decreased the objective by 2, and we are kind of at the objective 1 from 3. And only one of this penalty variable is set to 1. The other one, xi2, is already on the right hand side, and xi4 is actually on the left hand side, but it is taking the value 0. So let's actually repeat this process one more time. And this time we are going to select the W6 variable, because that one over here has the negative reduced cost or the negative coefficient. So if we do that, then where exactly can we increase W6? So the W6 appears over here. So here we can increase it all the way up to 1. We move the W6 to the left hand side, xi1 to the right hand side, and it will look something like this, right? So if we substitute it in the other equations, then it will look something like this. So in this case, we have another solution, which was the previous solution that we discussed, right? So W6 is 1, W5 is 1. That was our solution. And for that, we reached to the place where the objective is 0. So notice that throughout our solution process, only few variables which were on the left hand side, they took the value 1, or rather non-zero values, right? So the idea of the column generation comes from this fact that most of these variables are not even needed. Okay, so what we do is we start out without any of these W variables, and we only add them when they are needed. So how do we add them? It's basically that process is the column generation process. It's like there are still a lot more jargons that I'll need to introduce if I want to explain it completely. But the idea is that it is actually generated using another integer program. That sub problem will minimize or maximize or all possible W variables and find me the one that has the smallest possible reduced cost. And if that is negative, then I can actually add it to my linear program, and that might actually result in that variable being brought to the left hand side. And so we essentially handle this issue of having too many of these W variables by this way. So we don't just simply add them, we only add them when they are needed. So that is the original idea behind the column generation. These variables are generated using the sub problem. And these sub problems are essentially most of the time small linear integer programs. Sometimes they are not linear integer programs, or sometimes they are completely different type of optimization problem. But for our case, we are going to focus on sub problems which are linear integer programs, because that's what happened in both of my projects. Okay, so now you understand the idea behind the column generation and everything. So now let's talk about another application where column generation is used, which is decision trees. So what are decision trees? Decision trees are another type of classifier which looks something like this, right? So we have a bunch of nodes. So these are called internal nodes, and these are called leaf nodes at the end, right? So the internal nodes will have some sort of a question on the features. So our data set has a bunch of features, let's say A, B, C, D, E, F, G, all those are our features. And these internal nodes have some sort of questions on them, which is like, say A is less than 4, then go to the left branch, otherwise go to the right branch. And on, let's say, left branch, we have another question, which is if B is less than 3, then go to this left leaf node, otherwise go to this right leaf node. And the leaf nodes will have essentially the targets, right? So here we have just two targets, which is right and wrong. And so the goal is that we want to generate something like this. So we have our data set, we have this structure. All we need to do is we have to figure it out. What should be this, this kind of questions? We'll call them split checks, right? So what should be the split check at this node? What should be the split check at this node, and what should be the target values for all of these leaf nodes? So Firat and others actually proposed one column generation based heuristic for generating this kind of decision trees. So let's actually talk about it a little bit, right? So let's consider this smaller problem, right? So we are not going to optimize over all possible split check, but let's say we have taken out some candidate split checks for each and every node, right? So this is like, this is how one split check will look like. So we have, for this node, we are going to consider 1, 2, and 3 different split checks. For this node, we are going to consider 2 different split check, and here again 2 more split checks, and target values are kind of like, we have to consider all target values for each leaf node. So the idea is that we want to optimize over this candidate split checks and figure out how we can select the ones which will give us the best accuracy. So this is also an optimization problem, and Firat and others actually solved it by using this kind of variables, right? So they formulated this entire optimization problem using this kind of path variables, where there is a path from root node to leaf node, and each node has assigned something, right? So this node is assigned this split check, this node is assigned this split check, and this leaf node is assigned this target value. I'm going to describe all the constraints and how the master problem is generated and how the sub problems are and everything in my thesis defense. But the main idea behind this kind of work, where column generation is used for decision tree, it comes from the variable design. So if we think about how many path variables are there, then we'll realize that there are just too many variables, right? So just for this highlighted nodes, how many variables are there? So we can pick any of these 3 split check for this node. We can pick any of these 2 split check for this node, and any of the 2 targets for this leaf node, right? So it has 3 into 2 into 2, that is 12 variables just for this leaf node, and we have 4 different leaf nodes. And if we consider even bigger size trees, then it will increase even exponentially, right? So there are just too many of these variables, and we cannot really have linear programs with that many number of variables. So these variables are essentially generated using column generation, and I'm going to explain all of that detail in my thesis defense. So let's talk about what actually I worked on, right? So very briefly, I'm going to introduce the topics that I worked on. So my first project actually involved using Boolean decision rules that we just discussed before, right? That Boolean decision rules we wanted to use for a multi-class text classification problem in the real world, right? So Boolean decision rule can only output true or false, and so that they're essentially binary classifiers, and we wanted to use them in multi-class text classification problem, and that actually introduced a lot of different issues. So that was my first project, and in my thesis defense, I'm going to talk about that. So my second project was about the decision trees, which we just looked at. Initially, Firat and others came up with this column generation based heuristic, which I'm going to again explain in my defense. And I'm also going to explain how I changed that entire model, like master problem and sub problem, to make the training process a bit faster. So that was the second project. And my third project was a software framework for building all sorts of classifiers that use column generation. So I learned basically a lot of things about column generation. I faced about a lot of different issues while implementing these 2 different classifiers. And this framework essentially makes it easier to create new classifiers that are based on column generation. So it also includes some of my work on reoptimization for the subproblems. So the subproblems are essentially very, very similar to each other. Only the objective part is changing. So my competition work, which was about solving mixed integer programs which are similar to each other, that is also kind of partly implemented in this framework. So I'm going to talk about that as well. So I think I have covered most of the prerequisites that are needed to understand my thesis defense better. And I hope that some of you might be able to join me for my defense. So if you are interested in attending my thesis defense, please fill out the form in the description and I'll send you the link whenever it is finalized. So that's all for today and see you in the next video.